Okay. Good morning, good afternoon, and good evening, honorable judges, respect audience, and fellow participants. Let me begin by introducing myself. My name is Ahmad Syahputra, and I am currently a student at Erlangga University, majoring in mathematics. Today, I will be presenting a project entitled Analyzing Global Temperature Change using the second order Taylor series approximation. Through this project, we aim to demonstrate how mathematical modeling, particularly Taylor series, can be applied to understand real-world environmental change. This slide shows the background of our project, focusing on the change in global surface temperatures anomalies over time. As you can see from the graph on the left, global temperatures have experienced natural fluctuation since the year 1880. However, starting around the mid-20th century, the long-term trend clearly show a consistent and steady increase in global temperatures. The graph on the right zoom in on the years 2000 to 2023. Here, the warming trend becomes even clearer. Since around 1980, the rise in temperature has accelerated significantly, and in recent years, anomaly have reached more than plus 1 degree Celsius compared to the historical average. This persistent upward trend in temperature anomalies serve as a strong indicator of global warming, and it provides the foundation for why we choose to analyze the problem using mathematics, specifically Taylor series approximation. On the left side, we have the main objective. First, to analyze global temperature trends using historical climate data, and second, to predict future global temperature through a mathematical approach using the Taylor series. On the right side, we define two specific objectives to explain how the Taylor series can approximate temperature as a function of time, and to compare the result of the Taylor series approximation with real temperature anomaly values from NASA's data. These slides highlight the main benefit of our project. For the first, it provides a quantitative understanding of climate change. And the second, it helps visualize and predict future climate. And the third, the project encourage interdisciplinary science. Now let's move on to the mathematical foundation of our project. The Taylor series is a mathematical method used to represent a function as an infinite sum of terms, where each term is based on the derivative of the function at the specific point. The definition is brought by Sinaga et al. 2024. The general formula of the sinus is the base below fx equals to fr plus the first derivative of fr over 1 factorial x minus r plus a second derivative of fr over 2 factorial x min a square and etc. This expression can be written in sigma notation like this, with f and a being the and derivative of the function f 8.a and factorial being the factorial of n, or the factorial of n is the product of all integers from 1 to n. The slide explain the data source and basis of our case study. We use data from NASA GISS surface temperature analysis, also we known as GISTEMP. This dataset provides global annual temperature anomalies from 1880 to 2024. The term temperature anomaly refers to how much the temperature in specific year differs from a baseline average. In our case, the reference baseline in the average global surface temperature from 1951 to 1980, which is 14 degrees Celsius. So, for example, if a Catania has an anomaly of plus 1.2 degrees Celsius, that means the global temperature that year was 1.2 degrees Celsius higher than the uh, 1951 to 1980 average, like that. Okay, this table presents the global temperature anomaly data that we use for the mathematical analysis. We select data for the years to 2000 to 2005, 2010, 2015, and 2020 based on NASA's GIS-TMP dataset. Here's what the table shows. In 2000, the anomaly was plus 0.39 degrees Celsius. In in 2005, it increased into plus 1.68 degrees Celsius. By 2010, the anomaly was plus 0.73 degrees Celsius. In 2015, it rose to plus 1.9 degrees Celsius, and in 2020, it reaches plus 1.01 degrees Celsius. Okay, in this slide, we present the mathematical model used to estimate global temperature anomalies using the second order Taylor series. We define the global temperature anomaly function as Tt equals to Ta plus the first derivative of Ta over 1 factorial T minus A plus the second derivative of Ta over 2 factorial T min A squared. Here's what is the means. Tt is the temperature anomaly at any given year T. A equals 2010, which we choose as the midpoint of our theta. Ta equals 0.73 degrees Celsius is actual anomaly in the year 2010 based on the dataset. For the first derivative of dA is the rate of change, how quickly the temperature is rising. And the second derivative of dA is acceleration, acceleration, how the rate of warming is increasing over time. We know that Fx plus h equals to Fx plus h times the first derivative of fx plus h squared over 2 factorial times the second derivative of fx and etc. And for fx minus h equals to fx minus h times the first derivative of fx plus h squared over 2 factorial times the second derivative of fx and etc. So the difference between these two equations can be written as like this: fx plus h minus fx min h equals to 2h times the first derivative of fx plus 2h cubic over 3 factorial times the third derivative of fx and etc. So the we get the first derivative of fx approximately equals to fx plus m minus fx min h over 2h. And if we add up the two equation or the previous slides, we get fx plus h plus fx min h equals to fx plus 2h squared over 2 factorial times the second derivative of fx and etc. So the second derivative of fx approximately equals to fx plus h plus fx min h minus 2fx over h squared. So we can calculate the value of the first derivative of t at 2010 and the second derivative of t at 2010. So the function t can also written as tt equals to 0.73 plus 0.022 t minus 2010 plus 0.0006 t minus 2010 squared. In this slide, we present a comparison between the actual temperature atomic data and the prediction made using the second-order Taylor approximation centered at the year 2010. As you can see in the table, in 2010, the predicted value exactly the same as the real data, 0.73 degrees Celsius, since this is the point we use the reference in the Taylor expansion. For the years 2005 and 2015, the data value are fairly close to actual data, showing good agreement. In 2000, the pages slightly overestimate the anomaly. In 2020, the predicted value matched the real data again, suggesting that the second order time approximation can be quite effective for the short-term prediction. Overall, this comparison have us evaluate how well the mathematical model capture the real-world behavior of temperature change. Okay. Okay, the slide show our future temperature automatic prediction using the Taylor series approximation. In 2030, the global temperature anomaly is projected to reach 1.41 degrees Celsius. By 2040, it could rise to 1.93 degrees Celsius, which means we are expected to exit to 1.5 degrees Celsius threshold will well before 2040. And in 2050, the anomaly could reach as 2.57 degrees Celsius. So, what does this mean? Firstly, exceeding plus 1.5 degrees Celsius is critical climate tipping point, and this could happen in less than 2 decades. Secondly, if current trends continue, temperatures may drastically, potentially up to plus 9 degrees Celsius by 2100. This change will likely have serious consequences on global climate patterns, increase extreme weather events, disrupt ecosystem, and threaten human health and livelihoods. The emphasis the urgency for climate action and better predictive tools to inform policy and mitigation strategies. So, to conclude, the Tyler series has proven to be a powerful tool for analyzing and predicting global temperature change. I have done with limited data, just anomaly values and a few derivatives, we are still able to project temperature trends decades into the future. And the third, the positive second derivative is our calculation reveals that global warming is not just continuing, but its rate is accelerating. And the last, ultimately, this project highlight how mathematics and calculus can go beyond the classroom, serving as an educationally a tool and a call to action for the environment. As education for future research, we recommend considering external factors such as carbon dioxide levels, El Nino phenomena, or human activity that might significantly affect global temperature. Additionally, using high-order Taylor series such as a third or fourth order can potentially increase the accuracy of the prediction. Actually, we believe this project has great potential to be used in education to bridge the gap between abstract mathematics and real-world issues like climate change. Okay, this is my reference source in searching for data. Thank you for your attention.